you hear me? Loud enough? No? Okay, but I don't think I can change the volume. Is this better? Yeah. Okay. Yeah. Okay. So I want to thank very much Phil and Ludmil for inviting me to come here. I'm sorry I could only come for a few days. I'm going to do something which I don't usually do. Oh, Herb's doing. Can it be louder, maybe? Yeah. Oh, it's pointing wrong. Does this help? Yes. Yes? Okay. That's good. Okay. All right. So I'm going to do something which I don't usually do, which is talk about some, in quote, very old work of mine. So one of the very first papers that I wrote almost 20 years ago, when I was still a graduate student. There's two reasons for it. The first is that I never really actually talked about it back then in front of an audience. And then second, it fits very well with this theme of Lefschetz because it connects to Lefschetz description of cohomology of smooth projective varieties in terms of hyperplane sections. Okay, so the title is going to be see this, if you touch this long way, primitive cohomology at the tube melting. Tubes. Okay, and so let's start. Just very briefly, I'll say what Lefschetz proved about the cohomology, right? So we'll take some x that sits inside of Pn, smooth projective, dimension x is n, not in any hyperplane. And then if I have a hyperplane in Pn, I can intersect that, right? So I can look at S, which is H intersected, and we'll have dimension n-1. And Lefschetz tells us that as long as S is smooth, a lot of the cohomology of X and S are the same, right? So Lefschetz shows that the Lefschetz theorem is that the restriction map on cohomology from X with integer coefficients to cohomology on S with integer coefficients. This is an iso if K is at most n-2 and it's injective. Okay, equals n-1. Okay, and then so this basically says that X and S have the same cohomology in low degrees. By duality, I can also propagate this to high degrees. And then it leaves two pieces of the cohomology that where they don't explain each other. So the two pieces are, I have the primitive cohomology. For the primitive cohomology. So this is the cohomology of X in degree n, and I'll indicate the primitive by a 0. So this is the kernel of the restriction. If you touch the pin, okay. So this is the kernel of the restriction map from Hn xc to Hn sc. That's the part of the cohomology of X that I cannot see in terms of S. And then for S, I can turn it around. There's the so-called vanishing cohomology in degree n-1 of S with integer coefficients. So that's the kernel of the Giese map. I lower star from Hn-1 S to Hn+1. Right, and this is dual to the map of homology. Like this, right? So those are the two pieces. So if I care about explaining X in terms of S, then the missing bit is the primitive cohomology. If I care about understanding S in terms of X, then the missing part is the vanishing cohomology. Okay, and so now what I want to do is give a way to describe this missing piece, namely the primitive cohomology of X, not in terms of a single hyperplane section S, but in terms of all hyperplane sections at the monodromy action on, right? So the goal is describe the primitive cohomology using monodromy. So there's going to be like a topological construction that that I learned from her, and this is where this tube mapping comes in. Okay, so so my notation will be, to abbreviate a little bit, I'll just write P for the projective space, and then I have the dual projective space. So this is the set of hyperplanes in P. For each of these hyperplanes in P, I get a hyperplane section, and then I have the dual variety or X check. This is the ones where it's singular. So these are the H's in P check, such that H intersected X is singular. And so on the complement of that, on P dual minus the dual variety, I have a universal family, the universal hyperplane section. I'll just call it, I don't know, script S or something like that. Okay, and then because all of these different guys are diffeomorphic, you have the monodromy action. So if I have G, the fundamental group of that quasi-projective variety, then this acts on the cohomology of, say, some particular reference surface. And maybe I can also act on the Lefschetz cohomology. Say this is some base point. I have some particular base point H0 here, and S0 is that. Okay, that's the monodromy action. And now it turns out that with this monodromy action, we can actually create new cohomology classes on X from cohomology classes on the surface. So this is where this tube mapping comes in. So this is an idea by Herb, I think, or at least when I was a student, I learned it from her. So what we're going to do is we start with the homology class, and I'm just going to describe it in homology first, okay? So we start with the homology class on this reference surface. So this is an n-1 cycle. And then we're also going to take an element in the fundamental group. So this is a loop in P check minus X check.
What's the subscript 0?
It just means it's a reference hyperplane section, some base point in. Okay, and then let me assume that this class here is invariant under the monodromy action. Okay. Okay, so now let's say I have some initial segment of my path G. Say here's time t equals 0, here's some later time, and here's maybe my cycle alpha 0. Then I can parallel transport that cycle along this path, and it will sweep out some kind of tube-shaped structure like this.
These are the slices that are transversal.
These, yeah. So the X check is the one where they're not transversal, and I'm only looking at the set where they're transversal. Okay, so at some reference time here, this gets transported to some other cycle on this other fiber, and the fact that the thing is monodromy invariant says that when I come back to the original point, the two things are homologous, right? So what this gives me is by transporting along this path, by parallel transport along the path. So this gives me an n-chain gamma on X, whose boundary is, well, the initial cycle that I started from and the cycle that I get to at the end. And the fact that it's monodromy invariant is saying that alpha 1 minus alpha 0 is also the boundary of an n-chain on S0, where gamma is an n-chain on S0, right? And so then if I take the difference, this is now an n cycle. On X. Okay, so I take this tube by transporting the thing, I add some cap at the end to make it close up, and then it gives me an n cycle on X. And so if I put this all together, there's this ambiguity in choosing the chains, but what I'm going to get is, so I'm going to get this tube mapping, which goes, well, from the sum of, so all the elements in the fundamental group, and then for each element, I have those alphas in the Yeah, actually, so I'm going to convert it to homology now. Let's do that. So this was the homology description. Now I take graduals everywhere. Then in cohomology, I'm going to map from the cohomology classes here that are invariant to the cohomology of X, and then I'm just going to project to this primitive part. Okay, and here I might as well take the vanishing cohomology, because it turns out that if you take other stuff that's not vanishing, you don't produce any interesting classes.
Can you draw the picture?
Of this too? Or?
First of all, I hate cohomology. I like homology.
Yeah, that's why I sort of try to draw it here. So imagine you have this path.
I got that picture, but I don't have the indices. N and N minus 1, I don't know what's what.
Okay, so imagine that, say, X is dimension 2, and this thing is.
No, I don't need an example. I mean, I need a picture of what you're talking about. I've got that picture up there of the cylinder to go around.
Yes. So this going around each of these loops lives in the different hyperplane sections, in the different S's.
Come back around, you don't have the same cycle.
You don't have the same cycle, that's right. But because I'm assuming that the cycle has.
How do you go between N and N1?
Okay, so I have N minus.
I don't
but
see
listen.
two different homology classes. I see two cycles and a homology between them.
Yes.
So I don't see why you can go from have anything to.
I have a path in the base. I transport these N-1 cycles along the path in the base, and in the process, they sweep out an N cycle, an N chain on X. When I go back and I come back to the initial point, I don't come back to the same cycle, but I come back to something that has the same homology class.
Okay.
So I can combine those two different cycles.
Oh, so you put a piece there.
And put a piece there that makes it close up.
And then there's two, just because it's torus, and that's the other one. It's fine.
Then it closes up, right?
The picture is worth 1,000 words. Symbols are less.
Yeah.
10,000 symbols.
Yes, maybe you're right. Yes.
No, I mean, if you just draw that little homology in, I wouldn't know what he's talking.
Okay.
Oh, you assume it's homologous.
Yes, right. So the key assumption is here, right? I'm assuming that the thing is homologous in other words. Okay, and so then the result is, so this is the theorem which was suggested by Herb.
So they're not well defined either. Depends on choice.
Yeah, that's right. So it depends on this choice. So it is well defined in H lower n of X, modulo H lower n of S.
Yes.
Right? And if I dualize it, I go to cohomology, then it means exactly I end up in this primitive cohomology. In there, it's well defined. Yeah. Okay, so again, I think of it like this. So I have a pair of this, a loop in the base, a class alpha that's invariant under G, and I send it to this, what I'll call the tube class by doing this process, right? And the theorem suggested by Herb is that that really generates the primitive cohomology, at least if you work over Q, not integrally, right? So over Q, the tube mapping is surjective. Okay, so the entire primitive cohomology is generated by these graduals of tubes, as long as the left-hand side is non-trivial. So as long as the vanishing cohomology is non-trivial. Because there's examples of, sort of stupid families like conics where the vanishing cohomology isn't there, then you can't expect to generate anything. But as long as you have vanishing cohomology, you're going to generate it. That's the result. Different. Yes. Okay. Yeah, please.
If your theorem is stronger, couldn't you also fan sums of pairs alpha G such that sum of alpha equals sum of the alpha?
Yeah, you could, yes. There would be some other thing. There was some specific reason for doing it in this way, and that's why I sort of try to prove this theorem. Yes. So let me maybe say two small things about it. So first, back then when I wrote this paper, I had a lot of trouble getting it published. Just being a graduate student and this being a sort of a concrete topological thing. And And then, okay, so this took quite a long time, but then later I had the happy satisfaction that when I applied for an NSF grant once, I got a really nice positive evaluation coming back, and that positive evaluation said something like, this is a very ingenious construction, and it's so basic that both the statement and the proof could have been done by Lefschetz himself. So, so this is the connection with Lefschetz. Also, so this, maybe I'll just say it because again, I can't draw it very nicely, but
you have hypothesis.
So the hypothesis is that these hyperplane sections do have to have non-trivial vanishing homology. That has to be the case. So there's kind of simple examples where this fails. For example, all the cohomology of the hyperplane section might be the cohomology of the ambient projective space with flat quadrants or things like that. Then of course you can do this, but this has a different sort of interpretation, which again I cannot draw nicely, but so if I go here, so I have my P check minus X check, the smooth hyperplane sections. The same way that Nikita said it in his talk, over that I can make some kind of infinite covering space where the points in here correspond to the hyperplane sections, but for each hyperplane section, I can also record all the cohomology, right? So here I would have points which are a hyperplane S, and then the vanishing cohomology, say integrally of H intersected S with integer coefficients. I mean alphas in here. Right? Recording also all the different cohomology classes gives me some big infinite sheeted covering space like this with multiple different infinitely many connected components. And then from that point of view, what this two mapping thing is saying is these pairs G and alpha, such that alpha is invariant under transport by G, they exactly correspond to closed loops in this covering space T, right? Because this means that I have a loop in the base, but the invariance property is saying that when I lift it into this covering space, it stays closed up. Okay, so the interpretation of the tube mapping is that the topology of this infinite sheeted covering space is rich enough so that I can see all the primitive cohomology of X in the topology of this infinite sheeted covering. Yeah, that's the kind of interpretation. And then actually the statement that Herb was originally asking was much more precise, because here I'm using all the different infinitely many components of T, but Herb actually only wanted to use one specific component, the component that contains the vanishing cycles and Lefschetz pencils. And that is unknown at the moment. So, but there has been some work since then by Yulong Zhang. He's going to give a talk tomorrow on a different topic, but I wanted to mention that this is sort of the only other person who's worked on this problem, like trying to shrink the number of classes that you need to generate the primitive cohomology. Okay. All right. So I'm going to. So any questions? Yes. I think it is false on Z. I mean, I don't have an example off the top of my head, but I think I knew back then an example which fails. Yeah. So it will only be some finite index subgroup over Z, I think. Yeah, that's right. There's also, I mean, over Z, there's also the issue like with the vanishing cohomology. There's sort of two different models that you use over Z, and presumably it matters which one you use. Okay, yeah. So I will. So my plan is to give a kind of idea of how the proof works. This is all pretty sort of concrete stuff, so I hope it's suitable for a Friday afternoon. So the first thing that I will do is I'll reformulate this map sort of dually, right? So instead of trying to show that this map is surjective, I'll dualize it and I'll show that the dual map is injective. That's the formulation that's easier. So we're going to dualize. So the tube mapping will be onto only if the dualized map is injective. So if I dualize it using the intersection pairing, the primitive cohomology becomes the primitive cohomology again. But on the left-hand side, I'm going to get a product. And instead of having kernels of G minus the identity, I'm going to have co-kernels. Right? So the dual map is going to look something like this, that it's the primitive. it's the primitive cohomology of X, and then it's going to map into the product over all G and G, and then the vanishing cohomology modulo the image of G minus the identity. Okay, the kernel becomes the co-kernel generalized. And so it will be if and only if this is injective. And it's easier to show that some map's injective than to show it's surjective. And then this map here that I need to prove is injective, it naturally factors into 3 steps that kind of make it. So this factors into three steps. So the first step is, so I'm going to have a map that goes from the primitive cohomology of X to the H1 on my parameter space of just the local system, the locally constant sheaf on the vanishing cohomology. So this is the local system where the fibers are just the vanishing cohomology of the different surfaces. Okay? By all of these different vector spaces, they fit together into a local system on there. And this is just sort of an array spectral sequence kind of thing, right? So the cohomology of X is going to embed into the cohomology of the universal family of all of these surfaces. And then I look at, you know, how it restricts to the fibers, right? So I'm gonna have an injection from here into the cohomology of the universal family. And then by the array, first I'm going to map into classes on the fibers that I'm varying. So that's the check minus X check the local system of n cohomology of the fibers. But because these guys are primitive, they restrict to 0 on all the fibers. So here I go to 0. Right, so then you actually go into the next step in the array spectral sequence, which is this H1. Hn minus 1. This is the map. And then the Hn minus 1 decomposes into the vanishing part, plus the fixed part, which is just the cohomology of X in 1 degree less. But this thing here has no H1. It's just a constant local system. We are basically on P1. P1 has no H1. So that part disappears, and then I end up in here. Okay, so this is the first map. I go from cohomology of X to cohomology of this local system. And just by this array spectral sequence stuff, this is actually injective. So this map 1 is injective. Okay. The second step is the cohomology of the local system is actually just the cohomology of the fundamental group. So a group cohomology thing. So I have an isomorphism between the cohomology of that local system with the first group cohomology of the fundamental group on this Q vector space VQ, where I'm just using the notation. So V is the vanishing cohomology of the reference fiber over the integers, and VQ is just the rationally defined. And this is a G module, and this is a representation of G. Fundamental. This is just a general fact, right? So the cohomology of the local system in degree 1 is always group cohomology of the fundamental. And this group cohomology is always defined like this. So if I have a group acting on M on some G module, the group cohomology is very concrete. So it's all maps from the group into the module that satisfy this kind of co-cycle condition. Modulo those maps that are just given by G minus the identity. So modulo maps that look like G goes to G, V minus V, where V is in. Okay, that's the definition of group cohomology. Okay, and again, there's nothing special here. So this is just always an isomorphism by general principles. So I translate my problem to some group cohomology. And then the interesting step is the third step. So now I always have a map from the group cohomology, just the product over all elements of the group. And this thing here where just simply send one of those co-cycles to just its value at the different elements. Okay. And my claim is that by some kind of diagram chasing computations with cycles and so on, that the dual of the tube mapping is actually the composition of those theorems. Okay, that's something one has to check. Okay, if I compose the map to cohomology of the local system to map to group cohomology to with this sort of just algebraic map, that composition really is the dual of the tube map. The first map is always injective, the second map is always an isomorphism. It'd be very nice if the third map was just always injective, because then you just have it. But sadly, the third map isn't always injective, not for algebraic reasons, right? So, but 3 is not usually, injective. Okay, so I gave in my paper an explicit example. I'm not going to write it down for you because it's not very insightful to see it, but you can take the simplest kind of groups, just Z2, just the abelian group with 2 generators, and it acts in a 3-dimensional vector space by 2 explicit matrices, and you write this out and you see that the map is injective. Okay, so it's very easy to come up with such examples. So actually proving the theorem means we have to show that the map is injective in this particular case. For the particular groups that we get as fundamental groups of the complement of the dual variety, and for the particular representations that show up when you act on cohomology hyperplane. Okay, that's what you have to do. So the proof of injectivity, I'm gonna talk a bit about the structure of G and EQ. So I'll remind you of some of the standard results that, again, are part of this Picard-Lefschetz theory. And then those results can actually be used to prove injectivity. Okay, so what do we have? Okay, so any questions on? You good? Okay. So there's a couple of points. So the first thing that I'll do is I'll define a certain subset. There's a question? Yeah.
In the case of the 0, it's not first and breakdown. That's just obvious.
Yeah, it's
One of the first steps breaks
down. That is a good point. Yeah, maybe, I don't know, maybe. I wish I knew the answer. I actually don't remember what the answer is. I mean, it must be the first step that breaks down, but I don't really remember where or how it breaks down now. Sorry, this is a certain lapse of memory, I'm afraid.
They have some kind of condition. Include something. They have some kind of condition.
Okay, yeah, so the only thing I remember at the moment is there were some criteria that, you know, if the embedding into projective space is sufficiently positive in some precise numerical sense, then the vanishing cohomology will be non-trivial. I remember that, but I don't remember what happens here if it's not. Yeah. Sorry about that. Okay, what was I going to say? Right, so I want to describe the structure of this of V and of the monodromy, and basically most of it comes by looking at Lefschetz pencils, right? That's the basic thing. So, so what are we going to do? So I mean, it's known that so G, the fundamental group of the base, G is generated, meaning mapped onto by any Lefschetz pencil. Right, so a Lefschetz pencil means I have a line inside of my P dual that meets the X check transversely. And then I'll get finitely many singular fibers in that case, but they each just have one ODP, right? So you get finitely many singular H intersected S, but they have one ODP. And so the usual kind of picture would be that I draw this P1, then there are these finitely many bad points, and here's maybe my reference point S0. And so the fundamental group of P1 minus those finitely many bad points is generated by the loops around those points, right? So these kind of loops here, these loops will generate the Pi1. And their images in P check minus X check, they generate the fundamental group of X if I choose this P1 generic. Okay. Right, so the statement is that Pi1 of P1 minus P1 intersected X check maps onto the fundamental group G. Okay, and then at each of those singular points where I have this unique ODP, of course, I have a vanishing sphere. So in the nearby fibers, there's an Sn minus 1 that shrinks down to the singularity in the singular fiber. And those vanishing spheres, they generate some cohomology classes. I can transport them back to the cohomology of this S0, and there they actually generate the vanishing cohomology. So I have, I'm going to have a set delta inside of V, which remember is the vanishing cohomology of integer coefficients. So these are the classes of vanishing Sn minus 1s, I mean, rather they're Poincare duals from all Lefschetz pencils. Okay, and this actually, they actually generate this this V. So EQ is just generated by this delta. Okay, and then what do I get from these? So if I take any of these vanishing, so I mean, again, I can only draw like the simplest possible picture. So this is the picture that. So here, if you're in dimension n equals 2, then the singularity is going to look something like this schematically, and then the nearby one is a smooth thing, and here you have this vanishing S1 that shrinks to this point, right? That's a sort of high-dimensional version of it. Okay, and then locally, the way that these loops act on the cohomology by monodromy, that's given by the Picard-Lefschetz formula. So this one gives me a Picard-Lefschetz transformation. On cohomology, so I'm going to call this G sub delta. So this will go from V to V, and it sends a class V to. So it's V. Then there's some sign, the intersection pairing between V and this vanishing cycle, and then the class of the vanishing cycle. And the epsilon is, I think, -1 to the n times n minus 1 over 2, and this is the intersection pairing. Okay, that's the formula. So I'm writing this formula because you see that the structure of the monodromy is completely different depending on whether n is even or odd, right? This is the basic fact. So if when n is even, then the dimension of the S0 is odd. The intersection pairing is skew symmetric. So therefore, the pairing of delta with itself is equal to 0, and the G delta has infinite order in that case. When n is odd, things change completely because then the dimension of S0 is even. The intersection pairing is symmetric. The self-intersection number of this delta is plus or minus 2. And actually, G delta squared is the identity. All of these elements of order 2 in that case. Right? So somehow in the argument, when we try to show that this map 3, the map from the group cohomology to this infinite product, and I'm trying to show that that map's injective, you have to do two separate cases because the structure of the thing is completely different in those two cases. And it turns out that when n is even, no, sorry, when n is odd, the fact that delta has non-zero intersection number means that it's a pretty elementary argument. It's just a sort of linear algebra sort of thing, which is very easy. But the case when n is even is the interesting case. So I'm going to skip this is just a sort of manipulating some formulas kind of argument when n is odd. I'm going to skip that, but I'll try to explain how to prove it sort of conceptually in the case when n is even. Okay. Okay, so now the goal is show that this map to the product this is injective when n is even. Okay. All right. And so the key notion that we're going to need is so this is due to Janssen, Wilhelmus Janssen is his name. So he has some paper on this. So the notion is he calls this kind of structure that you have here a skew symmetric vanishing lattice. Okay, so we're going to have V, which again is going to be the vanishing cohomology of this reference fiber modulo torsion. So this is some free Z module, that's the lattice part. Then it will have a pairing on it that I'll just call B, where I'm just gonna take the intersection pairing times that sign to get rid of that sign. And then I will have a certain subset delta inside of V. So these are the vanishing cycles or the vanishing spheres. Each delta in delta is going to define for me this same transformation that I wrote earlier. So V minus B of V delta times delta, right? And then it's called a skew symmetric vanishing lattice if the following three conditions are satisfied. So first, delta generates V. Secondly, all of delta is one orbit under, oh, and what did I, yeah, oh yeah, sorry, I should have said it. Sorry, I need to, so I'm going to write gamma sub delta. This is just the subgroup of the symplectic group on V, the group of things that preserve this pairing that's generated by these G sub deltas. Generated by the G sub delta. So in our particular case, this is the image of the monodromy representation, right? It's the image of the monodromy representation in our case, because the group is generated by these loops in the Lefschetz pencils. Each of these loops by Picard Lefschetz gives me one of these transformations, so the monodromy group is generated. Okay, and then Janssen says it's a skew symmetric vanishing lattice if one delta generates V. Secondly, delta is a single gamma delta orbit. And then thirdly, there exists two elements, delta 1, delta 2, and delta that have intersection number 1. Okay, those are the three conditions. Okay, why do they hold in our case? So the first condition holds that it's just Picard-Lefschetz theory, right? All the classes of all the Lefschetz, of all the vanishing spheres in all the Lefschetz pencils, they just generate the vanishing cohomology. That's this basic topology of Lefschetz pencils. Why is it a single orbit under the monodromy group? Again, that's a basic result. That's due to the irreducibility of the dual variety. The X check in P check is irreducible, so I can move from any point along to any other point, and therefore I can move any vanishing cycle to any other vanishing cycle by monodromy. The interesting bit is number 3. So how can I find two different classes, delta 1 and delta 2, that have intersection number 1? Okay, so So for 3, so how to get 3? This is a kind of neat argument that's due to Janssen. Maybe I'll tell you this. This is very nice. I mean, this made me smile back then when I saw it, and it made me smile again now when I prepared the talk. So the way this works is you observe that in order to get 2 of these things, it's enough to find a singular hyperplane section, some singular S prime, which is H prime intersected X, that has an isolated singularity, which is not an ODP. An isolated singularity, but not ODP.
Not what?
Not an ordinary double point. It has an isolated singular point, which is more complicated than just a node, just a standard node, right? And the argument here is, if you have such an isolated singularity, and at that isolated singularity, you have the Milnor fiber, like you intersect it with a small sphere around that point, and topologically, that Milnor fiber is going to be a bouquet of spheres. If it's an ODP, it's just a single sphere, but if it's not an ODP, then the Milnor number is at least 2, and you'll have at least 2 spheres, right? These spheres, they will meet in a point, so it'll be a bouquet like this. And so as long as the Milnor number is at least 2, I have at least 2 of these spheres. Of course, since they intersect in a point, they're going to have intersection number 1. And then one can show that the cohomology of the Milnor fiber actually embeds into the vanishing cohomology. And so the images of those 2 spheres will be 2 classes that have intersection number 1. Okay, so this is the cohomology of the Milnor fiber can be embedded into this vanishing cohomology. Okay, so how does that help? So it means we need an isolated singularity which has Milnor number at least 2. And the way we find this is as follows. So we take a generic, or the way Janssen does it, we take a generic P2 inside of this P check. This generic P2 is going to intersect the dual variety in a curve, which is an irreducible curve, right? And if I pick this P2 generic, then the curve will have generic singularities, which means it can only have nodes and cusps. So here, if this is now the P2, the curve that I get can have some nodes, maybe it has some cusps, but those are the only sort of singularities that can show up. At a general point on the curve, I just have one ordinary double point. At a node, what happens is that I get these 2 different ordinary double points, but they stay 2 separate ordinary double points, right? So a node, so this has only nodes and cusps. A node means I just have 2 ordinary double points on the hyperplane section, but a cusp means that the 2 things of the nearby ones fuse together and make something with Milnor number 2. Okay, so the cusp means one singular point with mu equals 2. So you have to just argue that there has to be at least one cusp. Okay, and this is the pretty argument. So the thing is, if there was no cusp, then this curve would only have nodes. And here by what's it called? By the Lefschetz theorems again, the fundamental group is actually isomorphic to the fundamental group of the complement, right? Because I'm intersecting with the generic P2. So if the curve only had nodes, then it's known that the fundamental group of the complement is abelian, right? So if only nodes, then pi 1 of P2.
How is that now?
This is, I think, a theorem by Fulton. So this is some older result about the topology of curved complements. If it only has nodes, then it's. I don't know what the argument is. So I just remember the statement from Rob's book. Okay, but see, this cannot happen in our case because so if the complement is abelian, then because the curve is irreducible, then the fundamental group is actually a finite cyclic group. Right? And if the fundamental group is finite cyclic, then it means G is finite cyclic. So then all these elements in monodromy, they would have finite order. But in the even case, the Picard-Lefschetz transformation is infinite order. So this case cannot happen. Okay, so then this would imply that G is finite. So then this would imply that all of these G rows are finite order. But that's a contradiction in the even case. Okay. So this is how Janssen shows this third condition, that there's two vanishing cycles that have intersection number 1. And that's important because once you have intersection number 1, then you can start producing interesting invariant classes, right? Because now I have a class that intersects in some way with something. I can correct it by trying to subtract stuff and kill some intersection numbers. That's the point. So getting a 1 means that I can get rid of lots of integers by just subtracting. Okay, and then from this, Janssen shows by explicit computation. So this is a corollary again to Janssen. And the monodromy group actually has finite index in the. So the group generated by all the Lefschetz transformation has finite index in the symplectic group. And because of that, you can actually find, so if you said, if I write rank of V equals R, I can find R elements in this delta that give a basis for VQ, for the Q vector space, so they're linearly independent, such that just the monodromy group generated by those R things has finite index in the whole thing.
See, how did we get down to a curve? You mentioned curves.
I mentioned curves, yes. So in the traditional Lefschetz thing, you don't compute the fundamental group, you just say I get generators for the fundamental by intersecting with the generic P1, right? But if I actually want to get the honest fundamental group, I have to take a generic P2. And then the generic P2 will intersect this hypersurface X check in this curve, and it's the cohomology of the complement of the curve, right?
Where can a generic P2 curve?
Yeah. Okay, so is that really clear? So there's this neat kind of topological argument with the.
You mentioned something as finite order also.
Yeah, right. So here, if this group is abelian, then the pi1 is just the homology, and you know this curve in P2 has some degree d. I don't know whatever it is.
And, yeah. So something was a finite order.
Yeah, so if the fundamental group here is finite, then all the Picard-Lefschetz transformations are finite order. But in the even case, they all have infinite order. So
what's that? All the data does have finite order. What's that state? It says all the.
So the way, if G is a finite group, then the way it acts by monodromy, it will act by transformations of finite order.
Okay.
Right? But
why are we allowed to assume G is a finite group?
Because G is the fundamental. I mean, we're not allowed to assume it. We're saying it leads to a contradiction, right?
What?
We're saying that that's the contradiction. So the contradiction is the monodromy group cannot be finite because there's transformations in it that have infinite order. But if there was no singularity with Milnor number 2, then it would force the group to be finite. And that's what.
Why?
Well, because what I said, because the complement of a curve with only nodes is abelian. Fundamental group. No?
That's part of the logic I don't get. So, you're assuming, why does something have to be finite?
Okay, so you want me to say the argument one more time? So the logic is, suppose that there's no singularity with Milnor number 2. Then this curve where the generic P2 intersects X check only has nodes. It's a theorem that if you have a curve in P2 that only has nodal singularities, the complement is abelian fundamental.
Where's the word finite?
Yes. If the fundamental group is abelian, it's the same as the H1. And because the curve is irreducible, that H1 is then just a cyclic group of order, whatever the degree of the curve is. Okay? That's how it is.
But what H1 is finite?
The H lower one of P2 minus this irreducible curve.
Finite?
Right, because P2 is simply connected.
Okay.
Yeah.
Right.
Dang it, I came all the way from Stony Brook.
Okay.
Still a lot of Dennis questions to answer. Okay. Okay, right. Okay, so then maybe if we're good with this, I mean, this corollary kind of comes out of nothing, but it's just algebraic computations, right? So basically what Janssen does is, once he has this condition that there's these two cycles that intersect at degree 1, he's able to produce lots of symplectic transformations that lie in this monodromy group, and he's able to produce enough to generate a finite index subgroup. This is just explicit complications. Okay, so then I can tell you kind of the sketch of the proof after this point. Okay, so again, we're trying to show that this map here is injective to the product. Okay, so we're going to take some class. So we take some phi, which is a representative of this thing. Okay, so phi is a cocycle, so it's a map from the group into VQ that has this cocycle condition. And take it in the kernel, so say it's in the kernel. Okay, so this means that for every G in G, there is some element V that depends on G, such that phi of G is G times Vg minus Vg, right? That's what it means to be in the kernel. What I have to show that it's 0, I have to show that there's one element that I can choose that works for all of the G's at the same time. Okay, so being in the kernel of this is saying for every group element, there's a separate vector, and I have to find one vector that works for all of them. Okay, so then the first thing is, if this element G is in the kernel of the map from G to the monodromy group, right, this means that it acts trivially. Then actually phi of G is equal to 0. So such elements, they get killed, right? And the reason is just because, well, for this G, there is such a vector V, but G acts trivially, so then phi of G is equal to 0, right? So this is because you pick some Vg such that phi of G is G Vg minus Vg, but that's equal to 0. So the stuff that's in the kernel here, on that phi is trivial, so I can just disregard it. I can just assume basically that G is just this gamma delta. The kernel of the map doesn't matter because on that phi is trivial anyway. Okay, so then the second step is I'm going to pick this finite index subgroup. So I'm going to pick, as in the lemma, the elements delta 1, delta R in V, as in Janssen's lemma, so that the group generated by those transformations has finite index. Okay, and so for each of these deltas, I'm going to have the transformation GI, which is V minus V delta I. So this group is just the group generated by those transformations, those transformations, right? And so now I'm going to argue that I can make this phi trivial on this subgroup here, okay? On this finite index subgroup. So for each of these GIs, there is some VI in VQ such that phi of GI is GI VI minus VI, because phi is in the kernel, right? But the right-hand side, I can write in terms of the Picard-Lefschetz transformation. So the right-hand side is just minus this intersection number times delta I. So it's just a multiple, some rational multiple of delta I, right? And this makes it quite easy to find a vector that does all of these, because now that the pairing B is non-degenerate, so there's going to exist a unique V in VQ that achieves all of these numbers. So that B of V delta I, since they are bases, right, achieves all of these individual numbers that I want to get. Okay, because these guys are bases and the pairing is non-degenerate. And then if I correct my phi by adding this boundary to it, then this will now vanish on all the delta i's. This is now trivial on all the GIs. And therefore on the whole subgroup, on the subgroup which is the subgroup generated by them. Right? Once I'm trivial on a set of generators, then because of the co-cycle condition, I'm trivial on every element in that subgroup. Okay, so now by this argument here, I get a finite index subgroup on which the thing is trivial. And then you just observe that once you have a finite index subgroup, then you're good, right? So now this gamma, delta 1, this has finite index. So it means now if I take any delta in delta, and I have my G delta, then I know that for some power of it, so there's some m such that G delta to the m is in my finite index subgroup, and therefore phi is trivial on that power. Okay? But then, because of the way these Picard-Lefschetz transformation act, these act, so if I use the co-cycle condition, I can actually rewrite this using the co-cycle condition, and it just ends up being m times phi of G delta, because G delta acting on delta it just preserves delta, right? So here, once I act by G delta once, I get something in delta. After that point, it's just preserved by the element G delta. So each time I take an extra power of G delta, I just multiply this. Okay? And so then you see from this, because I'm working over Q, this implies that phi of G delta is equal to 0. So then I'm 0 on the generating set for the group, then you're 0 on phi is equal to 0. Okay, so that's the proof. But it is not at all an algebraic statement. It requires very much the structure of these skew-symmetric vanishing lattices, right? I need to know that I have certain specific almost generators with good properties that I can use. Yeah, okay, so I think that's the end. So thanks very much for your attention.